Hello again, chemistry students. We're now up to our final topic of the year for chemistry. We're going to finish up the chapter on acids and bases today by looking at the process called neutralization. You may notice that I am dressed in my lab protective gear. In order to understand this last topic of the year, it's important that you guys have a proper demonstration. And so I'm going to show you guys how to do a very useful chemistry technique known as a titration in order to determine the concentration of an unknown solution. And so today we'll be looking at a few things. First of all, we're going to see what chemical reactions of neutralization reactions look like. We'll also see how neutralization reactions are used in acid-base reactions and titrations. Also then, we'll see how properties of buffered versus unbuffered solutions compare. We do have some vocab. I will define what that is here in just a few minutes. However, we're going to go ahead and start with the notes. Once we're done with the notes, I will then show you guys the titration demonstration, and therefore you'll have a better understanding of what is going on. All right. Neutralization, if you look at the first part of the word, it has neutral. And so remember, neutral solutions are where the pH is 7 because you have the same amount of acids as you do base. And so what you typically have, and we'll see this today in the demonstration, we have hydrochloric acid. We're going to react that with sodium hydroxide, which is a type of base. And so we're going to end up forming two products. So this, as you remember from before, would be considered a double replacement reaction. And so the two things are going to form. We form a salt, which is good old sodium chloride, and we also end up forming our old friend water, H2O. So for a neutralization reaction, it's always an acid plus a base will form a salt, which in this case is sodium chloride, and water. And so the titration that we'll be doing today will involve reacting these two reactants together, and we will be forming these two products. All right. We're going to go ahead and talk about titrations, and I'm going to go ahead and I will demonstrate it to you today as well. You would have had the as a lab experiment, and so because of the circumstances, we were not able to have you guys do it. But I will go ahead and do what you guys would have done in the lab, and this would have been the final lab for you for the year. It's also sort of a rite of passage, as it were, so every chemistry student typically does at least one titration lab before they are done with the class. Using a small flask that contains some sample that we're trying to analyze, we have a long glass tube, which is referred to as a burette. And if you look at the burette up close, and I'll show you this in a few minutes, you will see that there are markings to indicate volume. And the volume that we're indicating in this case is milliliters. What we do, we have a known concentration of whatever, if it's an acid or base. We open the stopcock, and then it pours down into the solution. We also have to use what's called an indicator. The indicator will change color based upon whether it's an acidic solution or a basic solution. And so for today's lab and demonstration, we'll be using the indicator called bromothymol blue. And so we will be using that to help us with the problem. And so we will want to see the point at which the amount of base equals that of the H plus ion supplied, and so this is referred to as the equivalence point. And so we'll go through this again in just a minute. If you were to take a plot of the amount of, let's say, base added, and you take the pH, notice that we have what's called a titration curve. And so this is a graph of volume of acid or base added, which is down here. We're comparing it to the pH of the solution. We again use acid-base indicators. These are chemical dyes whose colors change based upon acidic or basic conditions. The equivalence point is when the moles of the hydrogen ion is equal to the moles of the hydroxide ion. And so, again, the reason we do this is because it's a useful way to figure out the unknown concentration of either an acid or a base. And so we're going to skip this problem for now. And so the reason we should care about neutralization is because it's helping our bodies maintain homeostasis. And so remember, one of the things in your body that needs to be tightly controlled is your pH level. And so there is a carbonate, bicarbonate system in your body that helps to regulate slight changes in either acidic or basic solution. And so we have in our bodies what are known as buffers. And so these are solutions that can resist changes in pH when limited amounts of acid or base are added. And so again, for our bodies, we have carbon dioxide, which we breathe out, combines with water. Notice that this has a double-headed arrow, so this is an equilibrium reaction, so it proceeds in both directions, both the forward and the reverse. We end up forming hydrogen carbonate, or also always known as carbonic acid, because again, there's the presence of the H+. This can also break down into a hydrogen ion and a hydrogen carbonate ion. In the older literature, this would also be referred to as a bicarbonate ion. And so when, for example, a person begins to hyperventilate, they breathe into a paper bag in order to recover the lost CO2 and to restore the pH balance. And so, again, buffers are useful for life because it does help them keep their appropriate pH. And so I'm going to go ahead and show you again what we'll be doing today for our demonstration. All right, so today I'm going to demonstrate to you how to perform a titration type reaction. Remember that a titration is a method used to determine the unknown concentration of a solution. And so in this case, we have an unknown concentration of hydrochloric acid. We're going to use a known concentration of sodium hydroxide in order to figure out what the unknown concentration of the acid is. And so again, this is going to be a neutralization reaction. We have hydrochloric acid, which is our acid. We have sodium hydroxide, which is our base. Together, these are going to form sodium chloride, which is a salt, and H2O, which is water. And so again, I want to point out the equivalence point is when the moles of the H plus equal the moles of the OH minus. Notice, if we look at this equation, we can see that it's already been balanced and we don't have to do anything more to it. Also, notice that all the mole ratios are 1 to 1 to 1 to 1. So to determine the volume and therefore the concentration of our own HCl is going to be a lot easier because everything here is 1 to 1 to 1 to 1. All right. Again, in order to see where this equivalence point occurs, we have to use what's called an indicator, which is a chemical dye. In this case, we're going to be using bromothymol. And so the main question that we're going to be asking in this demonstration, what is the concentration of 25 mils of HCl using 0.2 molar NaOH solution? So again, notice that our concentrations are always going to be in terms of molarity. And so I'm going to go ahead and take us over to our demonstration. So come along with me. Come along. Come along. All right. So let's see. All right. Very good. All right. I'm going to get over here. All right. Here I am. All right. And so again, we're trying to determine the unknown concentration of this amount of HCl. And so what we need to do is we have to use NaOH, and we're going to pour the amount of NaOH into this burette. So it's important to make sure that this is in the horizontal position so that you don't have to worry about it leaking out. That's why this is here as well. I'm going to go ahead and use a funnel. I'm going to place it here at the top. I'm going to take my known concentration of sodium hydroxide. So notice that this is 0.2 molar NaOH. And so I'm going to pour this into here. And so I want to pour it so that it reaches the top line here. And so I'm going to go ahead and do this first. So I'm pouring it in carefully. All right. Great. All right. And so notice that because I'm dealing with a strong acid and a strong base, I do have to make sure that I'm wearing my protective gear. And so I also need to remind you, I just forgot, you need to wear goggles as well. You don't want any acid or bases splashing up into your face. And so now we're ready to go ahead and get started. We have our unknown concentration of HCl. And so what I'm going to do, I'm going to take a graduated cylinder and I'm going to pour into this 25 milliliters. And then I'm going to put this into this Erlenmeyer flask. So I'm going to go ahead, take my HCl. I'm going to pour 25 mils into here, which is pretty close to that. I'm going to go ahead and pour the HCl into this beaker. I'm going to put this off to the side. I'm going to put this HCl off to the side. I do happen to know the concentration, and so at the end I will reveal what the actual concentration of this unknown was. All right, now we have our HCl, we have our NaOH in here. We now need to remember to add our indicator. And so our indicator here is bromothymol blue. We only need a couple drops, and so I'm going to unscrew the top. I'm going to take out my little squirter. I'm going to take just a tiny little bit, and so I'm going to add 1, 2, maybe do 3, 4. So I'll add a little bit more to this. And so I'm going to swirl this around. And so notice that when I swirl this around, there has been a color change that has occurred. And so this is telling me that this color for this particular indicator is in fact acidic. And so we will see a color change, and that will be the point where we have the equivalence point. And therefore we can use that to calculate the amount of the unknown concentration. All right, I'm going to put the acid right here. And so what I'm going to do, I'm going to add about a mil at a time, and then I'm going to take it out, and then I'm going to shake it up, and then eventually I'm going to come to a point when the color will not change when I mix it up, and therefore I will then be able to get the volume from this, and therefore be able to figure out from the equivalence point what the amount of acid is. And so I'm going to go ahead and add a milliliter to this. Notice that it has changed color, so I need to switch it up a little bit more. Notice it's kind of a yellowish pinkish color right now, and so I need to continue to add more of the base to this. And so again, I'm going to put a little bit more in here. So now I've added 2 milliliters. I shake it up. Notice again the color has not changed, which means I have not yet reached the equivalence point. Let me add a little bit more. I'm going to go ahead, shake it up. Notice again the color has not changed once I shake it up, so I still have to continue to add more of the base. I stop there, shake it up. Again, same color. I've added 5 milliliters now. I shake it up, still no color change. Take it out, I shake it up. Again, there's no color change. Take it out, shake it up, still no color change. Add a little more, remove it, shake it up, still the same color. Now we're at 9 milliliters of base added. Again, there's no color change. I'm I'm going to just add a little bit more. All right, I've added up to 12 milliliters. And so notice that the color has been starting to change. I'm going to add just a little bit more. Aha. And so notice that now there has in fact been a color change and I can't get rid of it. And so if I add more of this sodium hydroxide, notice that it's not going to change the color. So at this point, I have in fact reached the equivalence point. And so if I look at my scale, I will see that I'm at roughly 12.5 milliliters. And so what I'm going to do, I'm going to come over here to the board and we're going to calculate what the unknown concentration of this is. And so I'll have you guys come back over here. This is exciting, isn't it? Oh yeah, this is science. This is chemistry at its best. All right. So I'm going to go ahead, and so we're going to calculate then what is the concentration of the unknown acid. And so notice that we started with 0.2 molar of sodium hydroxide, and we also had 25 milliliters of HCl. All right. Remember that because you're dealing with molarity, molarity is moles per liter. And so if we wanted to solve for moles, we can rearrange it, so solve for that. So remember, molarity is moles per liter, or mole is the molarity times the liter. So in order to find the moles, I have to take the concentration, which is the molarity, and multiply by the volume. And so notice that I had 0.2 molar of NaOH. I see that it took 12.5 milliliters, and so in order to do this problem right, I need to convert this to liters. I divide by 1,000, which means I have to move the decimal place to the left 3 places, and so that's going to be 0.0125 liters. So notice this would move the decimal place 1, 2, 3. And so why I'm doing this is that I'm calculating the moles of the sodium hydroxide at the equivalence point. And so I'm going to go ahead and take out my calculator. And so with my calculator, I'm going to take 0.2 times 0.0125. I end up getting 0.0025 mole of the NaOH. All right, remember that at the equivalence point, the moles of the acid equals the moles of the base. And so notice that this amount of a base completely neutralized the amount of acid. And so if this is the amount of moles of NaOH, this also tells us the moles of the HCl. So 0.0025 mole NaOH equals 0.0025 mole of the HCl. And so remember, it's because we're at the equivalence point. All right, so we're at the equivalence point, so we know that the moles of this base is going to match up with the moles of this acid. All right, our final step then, remember that to calculate molarity, we take the moles and we divide by liters. And so notice we have our moles of HCl. We had 25 milliliters of HCl. We can convert the milliliters to liters, again, by dividing by 1,000. If we take 25 and divide by 1,000, we'll end up getting 0.025 molar, or liter, 0.025 liter. So the molarity of the HCl is going to be equal to 0.0025 mole divided by 0.025 liter. And so I'm going to take 0.0025 divided by 0.02. And so, 0.025 And notice that I end up with 0.1 molar HCl. So this is 0.1 molar HCl. And in fact, this was our unknown concentration at HCl. I turn it around, and lo and behold, the concentration of this HCl worked out to be 0.1 molar. So there it is. This is chemistry in action. And so with that, I'm going to go ahead and stop for the day. Make sure to do any of the homework. I hope you guys have a good rest of your day. And so we'll then review for the test, and this will be the final test then in chemistry over acids and bases. And I hope you all have a great